simple graph of 3 nodes. Independent set is that set, okay, such that you take that set, then you take any 2 elements in that set, there is no edge. Okay. So suppose you take just A, you just take A, then, okay, in this A set, there is no other element who is attached to A. So this is a correct independent set. You just take A comma B. This is not an independent set. Why? Because there are 2 elements in this set A, B, but there is an edge between them. Okay. Similarly, you cannot take BC. You cannot take AC. You can take individually B, or you can take C. Like this, you can do. Now, if you take a different graph, then you get a different independent set. For example, let's say in this graph, so V1, V2, V3, V4. Okay, you can think of, let's say V1. If you take V1, then probably you cannot take V2, V4 because they are attached to V1. So you need to take V3. This is one independent set. And another set is possible. If you take V2, then you take V4. These are the 2 sets that are possible. Now, in a graph, there may be many independent sets, okay, of different sizes. Okay, in this graph, for example, I can have an independent set of size V1. Okay, just V1. This is enough. But this is an independent set of smaller size. Okay, but this 2 are independent set of bigger sizes, like 2. Okay, so the idea with independent set is often it is asked this question that for a given graph, G, what is the maximum size of the independent set? What is the maximum size of the independent set? That means I have to not only find the independent set, but also its size. Size means here the size is 2, basically. And also, the size is 2 both the cases. So one, if I just give this set, this is enough. So the problem is find a graph for a given graph G. What is the maximum size of the independent set? So I have to give the maximum number and the set also. Okay, so that is the independent set problem, or often the maximum independent set problem. Okay. Now there are 2 terms in this context. I just mentioned, but because that second term is not of so important to us, but just in the context, there is a difference between maximal and maximum. Okay, maximal independent set or maximum independent set. Maximum is you can think of all kinds of independent sets in the graph G, and whichever has the maximum, whichever has the largest size, that is your maximum. Whereas maximal means you cannot, and you started with a particular vertex and you reached one independent set, okay, by exclusion and inclusion slowly. But you have reached one independent set now, which cannot be extended further by adding any further node. Okay, that is known as maximal. But maximal may or may not be maximum. Okay, but maximum is always the largest, basically. Maximum is always the largest, but maximal is actually sometimes maximal is maximum, but not always. It depends on the starting point, basically. Okay, but why these two definitions? One is maximal, one is maximum, because of some reason. Let us not go into that. We are interested in maximum independence. Okay, so now with this introduction, we take one simple graph and where we want to find out this maximum independent set. That means independent set of maximum size. Okay, so the graph that we consider is a simple graph of three nodes. Okay, and they are connected in this manner of a chain. Okay, and let's say the vertices are v1, v2, v3. Okay, so what we can do is we can have our algorithm like, so the problem is clear, right? Find out the maximum independent set in this graph. Okay, this is my G. So what I can do is I take this vertex V1 as a starting point. As soon as I take V1, I cannot take V2 because the V2 is neighbor of V1. So if I cannot take V2, I mean, it will not give an independent set, but I can take V3 because V3 is not attached to V1. So one possibility is I declare that V1 comma V3 is the independent set. The other possibility is I take this V2 only. Okay, I take this V2, and once I take V2, I cannot take V1 and V3. I cannot. So therefore, this is another independent set. So what is the maximum? This is the maximum size of 2. This is size 1. This is not of interest. So if I include this chain a little larger, okay, little larger. Let's say this is odd number of vertices. If I take even vertices, then what happens? This is my V1, this is V2, this is V3, this is V4. Okay. So I start with V1. Okay, I start with V1. Then I cannot take V2, but I can take V3. And then once I take V3, I cannot take V4. That is one possibility. The other possibility is I take V2. Once I take V2, I cannot take this V1 and V3. So I can take V4. Okay. So these are the possibilities. So these two are the possibilities, and this has a size of 2. This also has a size of 2. Okay. So if I take another chain of size 5, so you can think of in general chains of size odd or chains of size even. Okay, so if the chain is of size odd, okay, then what you can do is you can follow this principle. You can actually take the alternate elements starting from the beginning. So let's take an example. So this is the 5 elements. You can take alternate elements from the beginning. So you take this one, you take this one, you take this one. These 3. This is of size 3. You can think of you will skip the first one. You take an alternate. You take these 2. Then the size is less. So that is not important. Okay. So if there is odd, you start with the first element and take alternate elements. And if it is even, if the even number of elements, okay, something wrong. If you take even number of elements, so there are 6. So you can do like this. You take alternate elements either starting from the first place or starting from the second place. So either you take this one, then this one, or you take this one, and this one. Both are of same size. So depending on whether the number of elements in the chain is even or not, even or odd, you can choose the algorithm. That's fine. But so here, the problem is not so interesting. This is solvable, plain and simple. But now let us come to the actual problem that we are interested. Uh, actual problem that we are interested. Let us now make the problem slightly modified. Let's say I have n such vertices v1, v2, v3 up to dot 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 vn, and not only that, for every vi, I have an associated wi. I have an associated wi. What is wi? Wi is some weight I assign. Weight is each wi is suppose something non-zero, some non-negative number or weight associated with each vertex. So what is that? I have now the problem is slightly different. I have to find the maximum independent set such that, okay, you sum of the weight where I is belong to the independent set. So suppose you have formed one independent set and you find out the sum of the weight that is maximized. So not only the I mean, here the maximization criteria is something different. I mean, you have to take only those nodes such that the sum of the weight is maximized. Okay. I hope the problem is clear. Right. So let's say here W1, W2, W3, and so on, Wn. So every vertex has an associated weight also. Okay. So I have to find the maximum independent set that such that this is maximum. Okay. Now, what can be a solution? So one can say, okay, I will some sort of sort the elements, and I will take the beginning, take the elements from the top actually. Okay, but it may so happen. I give you an example that will lead to a contradiction. Let us take these three and let us say this has a weight of 10, this has a weight of 5, this has a weight of 4. Okay, so if I sort them, let's say, hello, if I sort them, then the numbers become like this. So I take the first vertex v2, okay, and then once I take v2, I cannot take v3 or v1, okay, and I declare that this is the maximum independent set. Okay, this is correct. But now, suppose I have changed the weight like this. This is my 6. Okay. Then if I sort, then my sorted numbers becomes like this. Then I take the vertex with the maximum weight. And once I take it, I cannot take V1, V3. But now I see that had I taken V1, V3, the total weight would have been 11, which is higher than 10. So therefore, V1, V3 is a better choice than V2. Okay, so that simple technique of just sorting the numbers, sorting the vertices based on their decreasing weight and take the highly weighted vertices into the independent set, that may or may not work. Okay, so you can think of that. Okay, I mean, so what is one successful? I mean, you can think of many other algorithms. I mean, some sort of ideas. Okay, but now we can give a naive idea, which is very crude. Is suppose I have a chain of n vertices. So basically, the trick here is which subset of vertices is an independent set, and two properties. One, it has to be an independent set, and the second is the sum of its weight has to be also maximum. Okay, so what I can do, if you think that I have a chain of n vertices, then actually I have 2 to the power of n subsets of vertices. Okay, so I have 2 to the power of n subsets of vertices, and once I have these 2 to the power of n vertices, sets of subsets, for each of them I have a weight. Basically, I can associate the total weight. So I can say, okay, there are say 1 Wi associated with these each of these sets. So there are actually 2 to the power of n weights. So what I do is I run a for loop. Okay, I mean for loop saying, okay, I mean from the top weight, from the highest weight, I can arrange these weights or these sets in decreasing order of their weights, and then I check what is the highest weight and the corresponding subset. Is that an independent set? Is that an independent set means then that set I have to check that in that set is there any pair of vertices who are adjacent, okay, to each other. If I find that at least one pair is there, then it is not an independent set. So I go down in the weight list. So that high weight, but it is not an independent set. That cannot be taken. Okay, so I throw it out. So in this way, if I carry on, then it can be done. But the problem of this approach is this is very naive. Okay, exponential time. And you need a sorting of exponential number of elements. Basically, you need to find out the weight for each of them and sort the weights in decreasing order. So you potentially need to sort the weights of these 2 to the power of n subsets. So you can think of it's something like sorting an array of 2 to the power of n elements. So sorting is exponential. So this is very naive but correct approach, but not quite acceptable because of its exponential nature. Okay. So a second question comes immediately, that how do we solve this problem? So one interesting idea, okay, is to notice it in the duplicity. in the subproblems. What is the duplicity? Let us consider this. Let's say this is V1, V2, V3, V4, Vn minus 1, Vn. Okay. Now, let us say we represent the optimal solution by opt of n. Why this n? Because there are n vertices, I put an n here. Now this I represent in some equation. I look at the last vertex Vn. Now I ask this question that is Vn is in the independent set or not? Okay. The answer is it may be in the independent set or it may not be in the final independent set, in the final optimal independent set. So what happens? So one case 1 is Vn is in the final independent set. So Vn is an element of opt, I can say. So in that case, what will happen? This Vn minus 1 cannot be in the final independent set. But the vertex before n minus 2 may or may not be in the final independent set. So what will happen? I will include Vn, but I cannot take Vn minus 1. But out of V1 to Vn minus 2, what should be included? That I do not know. So this part I can think of as a new subproblem. So I can think of, in this case, what is the weight function? Weight function is Wn plus opt to n minus 2. Wn is the weight of Vn plus the opt n minus 2. That means first n minus 2, what is the optimal weight? How do I find this opt? This is the recursive procedure. So opt n minus 2 plus Wn. Case 2 is when Vn is not in the final solution. If Vn is not in the final solution, then essentially the value is essentially opt n minus 1. So up to this n minus 1, up to this point, you can just discard Vn and you have this part. And in this subset, up to V1 to Vn minus 1, what is the optimal solution? That is the solution. Okay. So out of case 1 and case 2, these are the two cases when Vn, in case 1, Vn is not in the final solution, and the case 2 is Vn, case 1 is Vn is in the final solution, case 2 is Vn is not in the final solution. So in this, out of these two, which one you take? You take that one which gives you more weight. So you can write opt n is equal to max of these two. Wn plus opt n minus 2, comma opt n minus 1. Okay, so this is the recurrence equation for this problem. See, what is interesting here, if you look at the problem, what is opt n minus 2? Opt n minus 2 is up to this part. Okay, and what is opt n minus 1 is from V1 to Vn minus 1. Okay, this part of the subproblem. And if you look that this problem opt n minus 2 and opt n minus 1, these are subproblems which are very much overlapping, overlap up to n minus 2 positions. Okay, so this is a special kind of problem where the subproblems are highly overlapping, highly overlapping. Okay, so once I have this kind of overlapping, I have an understanding that probably this is a case of, dynamic basically. This is a case of dynamic. Why it is so? So before understanding that, we must understand, okay, I have formed such an equation. What is the good in it? What is the good thing in it? I may have to call this function recursively, but I mean, if you think of what I need to do, see Wn, I have all the Wn values. So what you can think of, you can create a tree structure, something like this. To get opt-n, you need to essentially have opt-n minus 2 and opt-n minus 1. You need to separately calculate this. To have opt-n minus 1, again, if I use the same thing, if it is n minus n, then it is n minus 2, n minus 1. Then opt-n minus 1, you need opt-n minus 3, opt-n minus 2. You need these two. So you see, here is opt-n minus 2, opt-n minus 2. Something very much common. Again, to compute opt-n minus 2 here, you need opt-n minus 4 and opt-n minus 3. And you see this opt-n minus 3 is there. These are common things. So if you go down like this, you will see many things are common. Many components are common. And those components you actually need not compute multiple times. You just compute once and you store them in a memory location, okay? And you use that at a later point of time, okay? So if I try to solve this recursive equation in a normal manner, in a normal recursive form, okay, like this recursion tree, then it will actually make exponential number of calls basically to these functions, and it will again be exponential in nature, okay? But what we use, I just told you, we do not repeatedly compute this redundant part. So we store that in a memory location, and that is called some technique called memoization technique. So basically the idea is you maintain an array for this particular problem. For other problems, we may need to have a different kinds of memory structure. So what we do is we maintain an array of this sort of this value. So we have an array. So what we have is we store in the first place we store opt1. What is opt1? When you have an array of one element, only single element, and there is what is the max. In the second position, we store opt2. Opt2 means what is the maximum weight when maximum weighted independent set when there are two such elements. Okay. See, for opt1, you do not need to calculate opt2. You just need to see whether this is higher or this is higher, and which one is higher, you take that. Opt3, again, this is opt3. Opt3 means there are 3 vertices. So either you take these two. It depends which one which one will lead to higher weight. Either this one leads to higher weight, or these two together leads to higher. Okay? So you have opt3. As soon as you have these couple of things, the next opt4, you can use this recursive formula basically. It is max of these two, max of opt2 and opt3. And opt2 and 3 are already in your table, in your array. So you do not need to compute. You just fetch from these values and you can compute opt4. Once you have opt4, opt5 you can do. So opt5 requires opt4 and opt3. So it requires, previous two values basically. Okay, it requires previous two things. So in this way, if you try to fill up this array, then eventually the last entry will be opt-n, okay, and that will give you the maximum weight of the independent set. So once you have that, then you are done. So, and remember, in this particular case, how much time we spend? We just need to fill up this array of size order of n. Each time inside, so it's a loop to fill up this array, and each computation of each entry in this array requires at most checking the previous two elements. Okay? So base cases can be actually fixed in a constant amount of time. And the next few cases, next all the cases, you can actually just, it needs lookup into previous computations. Okay, so you can actually fill up this array in order n time, and you can get opt-n. Okay, so this is the approach. So I will request you to convince yourself that it works. And there is one part left that I will just mention here, that this thing gives us the weight. Okay, this thing gives us the weight, but does not give us the set. Okay? But it is not very difficult to get the set, because once you know this opt-n, okay, you know really that out of the previous two values, so this is opt-n minus 1 and this is opt-n minus 2, which one you took in the opt, because you took the max of these two, right? And let's suppose this wn plus opt-n minus 2, that led you the max value. That means the wn is included in the set. So immediately, actually, you can note down that vn was included in the set. When you see that opt-n minus 1 was the maximum, was the cause of the maximum at any particular value of n, that means this n minus 2, this part wn must have been excluded. So you do not take that in the set. Okay, you just go for then opt-n minus 1, and during its maximum value computation, which one you took basically? Did you took this part or did you took this part? Depending on which resulted the maximum, you can actually, once you have this opt, that means you just scan through this array once more, okay, and you can actually backtrack the set. Okay? So basically, on part to compute the maximum weight, and another on part you can think of actually to recompute the set. Okay, so actually this can be actually put together. This can be actually done in a together manner. Okay, so that's why. So this is how we solve this maximum weighted independent set in a chain using dynamic programming. Okay, we stop here today. If you have questions, you can throw or post.